Here are your notes on acceleration. These should go on your acceleration foldable flap in your motion foldable. We will also fill in our last two graphs on the graph section. So the definition of acceleration is how fast or what rate the velocity changes. So we're going to be dealing with the meters per second or kilometers per hour per second, because meters per second themselves is a rate, and then how fast that happens is over seconds. And so we have a little bit more of a unit here that we have to deal with. So your answer could be meters per second or meters per second squared. You could also have something that's a rate, for example, kilometers per hour, over how fast it changes, which is seconds here. So kilometers per hour per second is an accepted unit for acceleration. So our formula for acceleration is the final velocity minus the initial velocity divided by time. We shorten that to VF minus VI, so velocity final minus velocity initial divided by time. We have a power triangle for this guy, and it looks right like this. So acceleration is equal to the change in velocity over time. So essentially the change in velocity is this symbol right here, delta V, or that triangle we call delta. That equals the change in velocity. That's velocity final minus velocity initial. So that is that right there. So the change in velocity over time is how we measure acceleration. So if we have an example here, a car takes 2 seconds from resting to reach 80 kilometers per hour. What is the car's acceleration? So we're trying to find acceleration in this situation. And what we want to do is identify our variables. So our time is 2 seconds. Our V final is that 80 kilometers per hour. So a lot of times people are going to get confused on acceleration problems because they're going to think they don't have enough information. But in this case, because it says resting here, we know that that's our V initial, and that resting means that it started at 0. So we do have enough information to solve. So I like for us to continue to work on writing out our equations. That will really help us make sure we're putting all of our variables in the correct spot. So if I'm solving for acceleration, remember I'm going to cover up the A, and then I look that I have velocity final minus velocity initial over time. So then I can plug in my information. So 80 kilometers per hour minus 0 kilometers per hour, remember, because I started at rest, over 2 seconds. And when I set that up, I get 40 kilometers per hour per second. And the reason why that's our unit is because none of these things cross out, which is okay because this is a rate, right? And it's how fast that rate happens, so that's over time. So 40 kilometers per hour per second. So again, to write your units the right way for our answer, it's really important that you work on including units in how you're setting up your work. So acceleration can be a change in direction, speeding up a positive acceleration, or slowing down a negative acceleration. So in our acceleration problems, you could have a negative number if you're slowing down. So do note that that is something that could happen. All right, to add to the graphs, so in this situation, this is a graph. We want to title it acceleration, an acceleration curve. So here we have our velocity on our y-axis and our time on our x-axis. So if we have an acceleration curve, right, over time, our velocity is going to increase until it's like that exponential graph here. So acceleration curve, go ahead and pause this and get this written down on one of your graphs. And then here is another graph. This is our, we can just simply title this acceleration curve as well, but it's got a little bit more information, so it's worth pausing this to make sure that you're writing this down. So here would be a positive acceleration, here would be 0 acceleration, so you're still moving, but you're not accelerating, so this is a constant movement, right? It's got velocity over here, right? So if I have velocity in meters per second, right, I'm still moving in a specific direction, but I'm not accelerating. And then here would be a negative acceleration. We could also call that a deceleration. So when you're all said and done, your graphs should look like this on the back of your foldable. So it's important to note here that in our speed, right, distance over time, a flat line is showing that we're not moving. But in our acceleration graph, a flat line means that we are at the same speed. So make sure that you have those labeled correctly. All right, from here you are working on your next acceleration practice problems